Okay, basically today I won't give you any new materials, so I will just review some of the concept that we have learned in our previous session. And then if you have any question relating exercise in maybe in this slide or maybe in previous slide, please do ask me in this session. Okay. We have learned about the Reynolds number. I hope you still remember. And then about the mass balance equation. I hope you also still remember. The other balance that also we have to pay attention in flowing fluid is the energy balance. Or in another term, we call it the Bernoulli equation. The Bernoulli equation is the simplest term of the energy balance. Basically, in flowing fluid, again, you need to be aware that there will be 4 types of energy. This is the internal, kinetic, potential, and pressure energy. Each have a relevant variable related to the energy. And how you express the energy, the unit can be in energy unit in joule, and then in specific energy, joule per kilograms, in head, in meters, or in pressure energy, in Pascal or ATM. But even if when you express the unit in different units, yeah, all are still form of energy. So you may need to pay attention. Suppose you have exam paper later, you need to pay attention what will be the unit of each energy and what kind of equation, what kind of parameters that you need to put into the equation to calculate that kind of energy. So Bernoulli is the simplest, the most ideal form of the energy balance. First, the assumption is the steady state. Yeah, the steady state is actually the assumption that we use when we derive the mass balance. Yeah, mass balance. Please remember that in steady state condition, with no reaction occurred in the pipeline, then you can say that along the flow, along the pipelines, you will have constant mass flow rate. Ya, sepanjang aliran Anda akan punya laju alir massa yang konstan pada kondisi tunak atau steady state. So at steady state, you will have constant mass flow rate. If the fluid have constant density, then you will have constant volumetric flow rate along the pipeline. So at any point, the mass flow rate will be constant, and if the density is also constant, then the volumetric flow rate is constant. And in Bernoulli equation, those steady state assumptions still need to be applied. But beside a steady state condition, Bernoulli also assume that there will be no energy loss, no energy input, and no energy output. So the component will comprise of pressure energy, potential energy, and kinetic energy. And you have learned how to write the equation. For example, this one is for the specific energy unit. So pressure should be divided by density. Height should be divided by, should be multiplied by gravity. And for the velocity square, this is the kinetic energy divided by the mass, so becomes these parameters. So Bernoulli equation is basically energy balance. In Bernoulli equation, you compare any 2 points, yeah, any 2 points. For example, this is A and this is B. So you compare point A and point B. Actually, as long as the fluid is flowing along the pipeline, you do not need to consider what happened during the pipeline when you derive the Bernoulli equation. You just need to pay attention at point A and point B. Yeah. While comparing point A and point B, you are comparing the energy transformation. Yeah, because one type of energy. For example, in this figure, the potential energy is increasing from point A to point B because the position of point B is higher than point A. So there will be increase of potential energy. It means since the total energy at one point should be similar to the total energy at another point, yeah, the total energy at point A is same as the total energy at point B, it means when the potential energy is increased, the other types of energy should decrease. And in this context, if we assume the pipeline is, the diameter is constant, it means the velocity, VA and VB, or UA and UB is also constant. And then only pressure energy will decrease. So you need to pay attention what kind of the parameters, whether it's pressure, height, or velocity that gonna be changing during the flow, or that gonna be increase or decrease between one point to another point. Yeah, that's the concept of the Bernoulli. You just compare at point 1 or and point 2, the total energy of each point should be the same. So if one type of energy changing from point A to point B, then another should change as well. But which one can be changing, which one can be constant, then you need to pay attention. You need to do, or you need to understand what kind of assumption that you can choose from the system. Okay, yeah. And by using the Bernoulli, then basically you can solve many types of situation. We have discussed about how if you have small hole in a very large tank, how to calculate the velocity at the bottom of the tank when the hole is appeared, or how to derive the equation for any types of pipe fitting. We have discussed about diffuser, reducer, sudden enlargement, and sudden contraction. If you only use Bernoulli, it means the flow is ideal between diffuser and sudden enlargement. The equation should be the same. I mean, if the diameter ratio between the small and the big one is the same, then you exactly will have the same value. And also, it's also the same for the case of reducer and sudden contraction. If you apply only Bernoulli equation, it means the condition, the assumption is ideal. There is no energy loss. But we have discussed that some fitting, like sudden enlargement and sudden contraction, will give more energy loss. Actually, we will discuss about the energy loss later after this chapter, but this is for the introduction. The energy loss from sudden enlargement or sudden contraction is higher because you will have more pattern change when the fluid comes from either smaller to the bigger diameters or from the bigger to smaller diameters, because the changing is sudden. So the change in flow pattern is also sudden, and it will create more energy loss to the system compared to diffuser or reducer when the diameter change is more gradual. Yeah, but if you do not consider if you do not consider the energy loss, so the flow is really ideal, then it should be the same. As long as you have diameter ratio is the same, the velocity at the inlet is the same. Then you have the same value of the velocity at the outlet, as long as ideal. Okay, and we also have discussed about the application of the Bernoulli for some kind of measurement device. What kind of measurement is the fluid flow rate? So the velocity or the volumetric flow rate, yeah, by using the Bernoulli equation. Depends on the arrangement of the equipment. For example, like pipette tube, it will hold the fluid coming to the smaller tube, the impact tube. So the velocity exactly at the mouth of the smaller tube will be equal 0. Then you can derive the Bernoulli. Basically, you just compare what happened in point 1 and what happened in point 2. What will be the assumption? What will be the condition? That you need to understand. And pitot tube, and then later the orifice, and then the venturi. I think the similarities will be the flow rate, fluid flow rate measurement is basically correlated using the Bernoulli, but the flow rate will be correlated with the pressure. Yeah, how to measure the pressure? Because in pitot tube, for example, you change the velocity, right? In point 1 will decrease to 0 at point 2. Same with orifice. At point 2, the velocity will increase since you have small opening. Also, it happened with the venturi. At point 2, the velocity will increase. But if you see these three arrangement, the position, the potential energy from point 1 to point 2 are the same, because the baseline for the height will be the straight line between point 1 and point 2. It means there is no potential energy change. So the velocity change will only correlate to the pressure. So if you have velocity decrease, it means the pressure will increase, and vice versa. In this one, point 2 will have 0 velocity, so we'll have higher pressure at point 2. While for orifice, you have higher velocity at point 2, it means you have lower pressure at point 2 compared to point 1. Then how to measure the pressure difference? You install the manometers. Although in here you can see the arrangement of the manometers, but basically in orifice and venturi, how you can use these two devices to measure the flow rate is basically to connect them with the manometer. So the manometer will read the pressure difference by reading the height difference. Okay, yeah, and then the other correlation I think you have learned. And for the rotameter, this is just for additional kind of fluid flow measuring device. But this one is more complex because the arrangement is a bit different. Yeah, it correlates the Bernoulli, of course. Basically, you derive the Bernoulli between point 1 and point 3 in this one. You will have height difference, you will have velocity difference, right? And also you will have pressure difference. So all three components of the energy will be different. And basically the pressure difference will be correlated with the buoyancy force that you have learned in our discussion at the beginning of the class. Ya. Jadi di rotameter itu sebetulnya nanti tekanan ini akan berpengaruh atau dipengaruhi dari gaya yang bekerja. Gayanya apa? Ada gaya apung, the buoyancy force. So the derivation of the equation will be a bit complex for you, so I do not write it in this slide, but just understand the concept. And in buoyancy, you will have the density, right? The density is the density of the ball and the density of the fluid. So last time, that's why we have to pay attention if we want to calibrate these rotameters. For example, if you want to use this rotameter to measure flow rate of oxygen, for example, then you have to calibrate it with the same gas, with the same fluid. So the measurement, the number that's shown by the bullets will show the exact value of the flow rate. Because in derivation of the buoyancy force, you will need the value of density. Okay. Any question relating these materials? Have you tried this exercise? Do you have any question? Or you can solve it easily? I hope you can solve it easily. Oke, silakan kalau ada yang mau bertanya. I Gusti Ngurah Waradana, are you there?
Yes, sir.
Have you done this equation, this exercise?
Sorry, sir, not yet. But I have a question about the static fluid, sir.
Okay, sure.
Wait, I can't send it. It's in the PPT. It's the manometer. It's the one where it goes the U sorry, the U loop is like up and down. Wait, I forgot which page. It's page 34 of the PPT.
Just a sec. Okay, you can share the PPT if you want. I give you access.
Oh wait. Wait, sir.
Okay, while Dana preparing the slide, just for the information for you that the first exam will be done next week on Thursday morning. So the same schedule with the regular class. I hope you don't have any class on Thursday morning, 7 to 9. Okay, this one, okay.
This one, sir, I don't understand how the top YouTube works.
Okay,
Like the
can you
pressure.
make this slide a bit bigger, Dana?
Wait, I don't know how.
Control Shift plus maybe because you open in the EduNext, right?
I
Oh
don't
no
think
no.
it.
Okay. It's yeah, it's okay. It's just a sec. Let me. Okay, your question is how to?
I don't understand the concept of like the YouTube above because I watched the recording again and this one is like for us to do it by ourselves. So you didn't explain it yet. I don't understand the how the pressure on the top tube
Okay,
works.
basically for the static fluid, you don't need to be confused whether the manometer is in downward position or upward position. So just remember for static fluid, because this one is all in the static condition, right? So you just need to remember any 2 point, yeah, P1 will have the same pressure at P2 only if the head is the same, yeah, and the fluid that connected these 2 points is the same. Yeah, this is the concept of the hydrostatic. So the water in the tank is pressurized by air. So even though this is air, the pressure here will not be atmospheric. Yeah, because it's not open air. Yeah, the pressure, maybe you still remember if you have a tank containing any fluid and if it's open at the atmospheric, so the pressure between the borderline between the liquid and the air will be atmospheric, right? But if the condition is like this, the tank is closed and you have air inside the tank, so the pressure at this point is not atmospheric. That you need to understand. Okay, so by the concept, at any 2 point, you will have the same pressure if you have the same head and the same fluid. So the pressure, the 2 point that have same pressure would be this one and this one. How about the pressure here?
Atmospheric, sir.
Yeah, this is atmospheric, correct, because it's open to the air. I hope the point number 2, because it's small at my laptop, at point number 2 is the level of the mercury and the borderline between the mercury and air, right? At point 2, yeah, the right side. Okay, so this point will be the same pressure at this point. Karena, because both are the same height, right? If you measure from this baseline. Oh, sorry. Yeah, because if you write down from this baseline, both will have the same height, and this 1 and 2.1 and 0.2 are connected with mercury. Will this pressure the same as this one? The height is the same, right?
Yes.
But will the pressure be the same? 0.2 and 0.3.
No, because it's different fluid.
Yeah, because when you go to 0.2 to 0.3, first you encounter oil and then you encounter water. Even though the heat is the same, but the fluid is not one types of fluid only. That's why the pressure P1 equals P2, then P2 will not be equals to P3. Then how to calculate the pressure? At point 1, I write down here, point 1 will be P at the M plus density of mercury, yeah, GH3. The one that you need to understand, the one that you need, maybe you need to memorize if you are still confused. If you go downward, yeah, from one point to any other point that's below that point, if you go downward, the pressure will increase. So if you go to point 2, this is P2, right? P at this one, this atmospheric, yeah, at this one. So at point 1, P1 will be P atmospheric plus density of mercury times gravity times the height 3. Okay, it will be the same as P2. P2 is here. Okay. How to calculate pressure at point 3? Because it's not the same as P2. So you need to calculate the pressure first at point 4. How to calculate point 4? P4 will be P2. So point 4 is higher than point 2. From point 2 to point 4, the liquid is only oil, right? So it can be written this one. So point 4 will be lower. Pressure at point 4 will be lower than pressure at point 2. So it will be P2 minus density of the oil times G times heat difference between point 4 and point 2. Sampai sini bingung nggak? Atau bisa dipahami?
Oh, wait, sir, I'm digesting it.
Yeah, you just go through one by one from point 1 to point 2, right? Let me erase. Yeah. So you just go from this point to this point. The pressure is the same. And then you go to this point. The pressure at this point will be the same as the pressure of this point, right? Because the heat is the same and the fluid is the same because it's all oil.
Yes.
Yeah. So this is the one that I explained previously. So pressure at here will be pressure at here minus rho G H here. The rho is the rho of the oil. So you get the pressure at this point. This is the same as the pressure at this point.
Oh, okay, sir. I understand.
Okay. Then you calculate. What is the question, by the way?
Finding the pressure of the air.
The pressure of the air. Okay. Okay. And then this is air, right? sorry, this is water, right? This is borderline between water and oil. It should be the same pressure between this point and this point, right? Because the head is the same, and this point and this and that these 2 points are connected with water. So the pressure at this point is the same. You have head different, then you can calculate the pressure of the air. So it's like moving backward, but moving backward from point this one, from this one. But if you go downward, then you have to add the pressure. So pressure below this, if you go from this one to this pressure, then you need to add. But if you go from downward upward, you need to subtract.
Okay, sir, I understand now. Thank you.
But please, I think this example got the solution.
Yes, but I don't understand why the sign is like that.
Oh, okay.
Previously.
Yeah, you just need to go. If you go downward, then you have P at this point plus rho GH, and then is the cursor visible to you?
No, sir.
No. Okay, let change to mouse again. Okay, is the cursor visible? No.
No.
Oh, then how to? Okay, just okay. If you go here, then the pressure is increased. Increase means you have to take plus sign, right? So it will be the same, pressure here will be the same as pressure here, then pressure here will be the same as pressure here. So if you go to from this point to this one, this pressure at this point will be less than pressure at this point, right? So you have to take minus. So this point will be the same as this point. And then you need to calculate pressure at the air. So if you go upward, then the pressure of the air will be the pressure of this point minus pressure minus rho GH of the water. I think that's one that you need to understand. So if you go deeper downward, then the pressure will increase. But if you go upward, then the pressure will decrease. Then you should not be confused when to use plus sign and when to use minus sign.
Okay, sir. Thank you.
Okay. Hope it can answer your question. Okay, any other question? Okay, while waiting for other question, okay, maybe I will not solve this exercise, but basically you compare point 1 and point 2. Yeah, point 1, the total energy at point 1 will be the same as the total energy at point 2. Yeah. P, I will use this one. So I forgot, divided by G or divided by rho? G, right? If you are using, let me check. Divided by G, okay. That's I always, okay. If I'm using the head unit, so you will have this one, right? U1 square. Yeah. But the one that you need to pay attention is between point 1 and point 2, there is height difference. Yeah. There is height difference. It means the potential energy will not be constant. So this one and this one cannot cancel each other. If you take the baseline at point 1, so Z2 minus Z1 will be how much? 20 centimeters. Yeah, this one. But please take, before you input the number, please use the same, the consistent types of unit. So if you want to measure with the SI unit, so please convert it into meters. Yeah, please convert it into meters. And then, how about pressure difference here? P2 minus, which one is bigger? P1 or P2? Can somebody guess?
Is it P1, sir?
Why?
Because the level of the liquid is lower.
Yes, correct. Yeah, so you can see from the height difference in the manometers, the right leg is lower. It means the pressure is higher. So P1 minus P2 will be the density of this, let's say, this is what? The mercury, right? Times this height difference, 0.2 meters. This one also 0.2 meters. Okay, you can have the value of P1 minus P2. You also have the value of Z2 minus Z1. Yeah. So if you take the value as the positive, it means for the height is Z2 minus Z1, and for the pressure P1 minus P2, because Z2 is higher than Z1 and P1 is higher than P2. How about the density here? This is the density of oil. It means 900 kilogram per cubic meters. Yeah, the density of oil. This is the density of, this is density of oil. How about the density of mercury? This one. So 13,600 kilogram per cubic meters. How about the correlation between this one? How you connect this one? Do you still remember? Okay, can anyone guess? Can anyone guess? Alika, are you there?
Yes, sir.
Yeah, how to correlate velocity at point 1? Basically, that one that you need to determine, right? You already have the value of delta Z, yeah, Z2 minus Z1. You already have the value of delta pressure, P1 minus P2. Then what you need to calculate is basically the volumetric oil flow. This is the Q, yeah. Okay, just Q1 will be equals Q2, right? In terms of cubic meters per second. Q is basically this one. Okay, you need either the value of velocity at point 1 or velocity at point 2. How to calculate the cross area? You just calculate this cross area. But how to correlate these two velocity? Do you still remember? Alika?
I don't really remember, sir. I'm sorry.
Seriously? Then I think you do not pay attention to the class. Okay, anyone can still remember? You have this arrangement. This is the venturi, the higher, the bigger diameters, and then goes to the smaller diameters. Besides Bernoulli, what other equation that you can use to correlate the velocity?
Reducer, sir?
Yeah, then what types of the equation? What is the law that you need to apply to get the correlation? Maybe not the value first, because the value you need to put velocity into the Bernoulli. But you can change either velocity at point 2 as the function of velocity at point 1, or vice versa. Velocity at point 1 as the function of velocity point 2. But to get the correlation, you need to apply what equation?
Steady state mass balance, sir?
Yeah, then steady state mass balance, you will have
The density, sir?
Sorry, I cannot hear you clearly. Can you speak louder?
The density, sir?
There?
With the mass?
Mm-hmm. Just a sec. Okay, so basically, you can use this one. Yeah. The flow rate at point 1 should be the same as the flow rate at point 2. Just remember the figure of the exercise. Yeah. So you will have this kind of correlation. You can change U2 into U1 or vice versa. Then you can put into the equation. Because you have the value of each cross-sectional area, right? 4.1, you can calculate the cross-sectional area is the circle with the diameter of 25 centimeters. And at point 2, it's a circle with the diameter of 12.5 centimeters. So you have the value of area. This one. This equation that you need to, wait. Yeah. Yeah, this equation that you need to use to correlate, this comes from the mass balance equation, correct? Then you substitute U2 as U1, and then you put in the Bernoulli. Then you get the value of velocity at point 1. If you get the velocity at point 1, then you just multiply with the cross-sectional at point 1, you get the value of volumetric flow rate. I hope you understand. You need to try by yourself. Then you will understand the context. Yeah, basically this is the same as the venturi, but this is the vertical types of venturi. So the derivation is basically the same. However, for this venturi, you will have height difference. The potential energy will not be constant. It will be increasing because point 2 is higher. Okay. Anyone has tried this exercise? Do you get the value? Ada yang sudah nyoba? Atau semua belum nyoba? Okay, I hope you later you can try in order to improve your understanding. Yeah, to improve your understanding, not just the exercise from this slide, but also maybe you can use the textbook. You can do the exercise in the textbook. I think for this one is basically the same, right? With the orifice, yeah. So you have opening, but yeah, it's supposed to be not here, but it's more closer to the orifice. But this one, the problem is you have not only one fluid in the manometers. You have A, B, C. This is the manometer fluid. Normally you only have one, right? Either maybe mercury or maybe oil. But this one you have 3 fluids inside the manometers. You have 4 with this fluid. Yeah. How to calculate the pressure difference? Yeah, let's say it's 0.1. This is 0.2. Basically, 0.1 minus 0.2 will be what? Anyone can guess? Have you tried this exercise? You need to try, then you will understand the problem. It looks simple, but later you will know there's some problems with this. Not that the question is incorrect, but since you have 3 types of the manometer, 3 types of the fluid in the manometers. If you have only one, basically the pressure difference. So if you have the same manometer, right? For example, this is the manometers, and you only have this one fluid. P1 minus P2 is only, let's say this is fluid D, but only one fluid will be equals this one, right? Delta H will be this one. Ya kan? This one. If you only memorize the equation, then you just go through this equation. Yeah, the pressure difference will be equals to height difference between 2 legs of the manometers. But that only happen when you only have one fluid inside the manometers, beside the one that flowing the pipe, of course. But if you have more than one, you need to derive it. You need to derive the hydrostatic equation first, because the one that you want to know is basically at this position, the pressure difference between these 2 positions, right? Okay. How about this one? Pressure at this point and pressure at this point. Is it the same or different? Kasia.
Yes, sir.
Yeah. And the red line?
Yes.
Pressure between the left manometer and the right manometer, will it be the same or different? And why?
Will it be different, sir?
Why?
Because of the different fluids.
Okay. If you analyze from the bottom, yeah, from, I think I'll use, okay. If you analyze from this one, it will be different, right? Because it goes through, let's say it's water, and then fluid A, and then fluid B, and fluid C. It will be different. Yeah. So don't say it the same. That's why, how to calculate then? Which pressure is the same? Di mana titik yang tekanannya sama? Which point? This point, right? This point. This point and this point is the same. Yeah. How about this point? Is the pressure the same? Muiz? Are you still there?
Yes, sir.
Yeah. The second red line from below, will the pressure between the left and right manometers same or different, and why?
Will it be the same?
Why? Because the head is the same, right? The head is the same, and it's connected to the same fluid.
But the fluid.
Yeah. I hope you all can understand. So the pressure here is the same. So you just need to this one and this one is the same. Then you just do the calculation of hydrostatic. You go upward from here, then you go upward from here. Yeah. Because you go upward, P2 will be lower than P at the right. P1 will be lower than P at the left. But this pressure at the left and at the right is the same. So you just go upward using the, so P1 should be P minus rho GHA minus rho GH water, right? Yeah. P2 will be P minus rho GHC minus rho GH water at the right. Yeah. Then you calculate P1 minus P2. Then later this can be cancelled out. This can be cancelled out. Ya kan? Nanti kalau dikurang-kurangi itu bisa hilang. So you just get this one. Okay, try by yourself at home. Okay, any question? Okay, if you have no question, I don't know whether you really understand or you have not yet do the exercise, but I hope you do the exercise later because next week we will have exam. So the exam will be from first lecture until this part. Although on this Thursday, I will give a lecture on the next part, but it won't be included in the exam. So the next part will be the friction calculation. The friction calculation will be for the second exam. Okay, if you have no question, then we'll meet again on Thursday. Thank you very much and good afternoon.
Thank you, sir.
Thank you.